All right, y'all, welcome to this video on linear regressions. We're going to continue to work on what we did in the last video where we look at data, we're able to plug it into Desmos, find out what the correlation coefficient is, and figure out the line of best fit. But I really want us to take a step back and understand the purpose of this, because this is one of the most useful things that we do in math class, is look at the relationship between two quantities. Researchers use this all the time. Mathematicians use this all the time. It is how we study the world. It is how we confirm our hypotheses. So imagine I'm a economics researcher, and I believe that one of the biggest predictors of how wealthy you will be as an adult is how much money your parents make when you're a kid. So my hypothesis is that children with wealthier parents are more likely to be wealthy as adults. That seems like a pretty sound hypothesis, right? But I need to be able to test that. I need to be able to confirm that my hypothesis is true. So you can imagine that I'd collect a bunch of data, right? Where I'd say, I'm going to collect your parents' income. I'm just going to call that PI for a second. Your parents' income, and then your adult income. And so you can imagine I'd collect data when someone's in 5th grade, and then I'd have to recollect data maybe when they're 30 years old to study that relationship. So this would be a long study. So let's say, this person had $10,000. Their parents made $10,000, and then they make $15,000. Another parent makes $100,000 a year, and they make $85,000. And so on and so on and so on, right? So I'd collect all this data from both of as on parent income and their adult income. And then I would put it into some software that runs regressions. And I'd have parent income on the x-axis. And I estimate that this will predict your adult income, or at least help predict it. And I plot the data, right? The data gets plotted all over the place. All right, and this is what it looks like. And it looks like I have a positive relationship here, which was my hypothesis, that children with wealthier parents are more likely to be wealthy as adults. Then we'd end up getting a line of best fit, and I could end up using this line of best fit. And I'd say, okay, there's a kid whose parents make $35,000 a year, right? $35,000. The line of best fit would predict how much money they make as an adult. Okay? And that's what we're going to be doing in this video. It's very, 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 very useful skill. I tell the example of the mathematician who found the relationship between, how many threes a team shoots and their winning percentage. That kind of changed the NBA forever. All right, so I hate that this is the first example, honestly, because it's not great, but we'll do it anyways. It's good practice. The table below shows the relationship between the amount of money in Bill's savings account and the amount of years passed. Predict how much money Bill will have in 10 years. So to make this prediction, we need to plug this data into Desmos. So let's start there. I'm going to open Desmos, clear out any data that I have from anything else, enter in a table, and you can do this with me quickly. After 0 years, Bill has $400. After 1 year, $450. 2 years, $505. 3 years, $530. 4 years, $580. And 5 years, $600. All right. I run a linear regression using y1 is almost equal to mx1 plus b. And I can see I want to make an equation here. I have a slope of 40. I'm going to round this y-intercept to 410. So I'm going to say, okay, the slope is 40, the intercept is 410. And now that I know the slope and the intercept, I can write an equation for a linear equation in slope-intercept form where m is the slope and b is the intercept. I can plug in and get y equals 40x plus 410. And if I want to be even better, I can replace some variables that make sense here. I can use money instead of y equals 40, and instead of x, I might use a y to represent years. Of course, I'll definitely want to define my variables. Say the dollar sign is equal to money, y is equal to years. All right, now that I have an equation, I can make predictions with it. That's the point of creating these equations. So I want to predict how much money will Bill have in 10 years. Well, 10 represents years. Y represents years in this equation. Variables are for unknowns. Years is no longer an unknown. So what I can do to make this prediction is I can plug it in. Plug in a 10 to the y, and I can solve. 40 times 10 is 400 plus 410. We predict that in 10 years, Bill will have $810 using a linear regression. Now, this is not perfect linear data, right? This is 50, this changes by 55, this changes by 25. But on average, how much does the linear regression predict he makes each year? We predict he's going to make about $40 a year, or add $40 to the account each year. And so that after 10 years, we predict he will have $810. The you do is a better question. I think this will get at the heart of the matter a little bit better. So I want you to try it on your own, right? We have data from my math class from last year. We have 10 students. 1, 2, 3, 4, 5, 6, 7. I lied. We have 8 students here. In one column, we have their attendance rate. In the other column, we have their grade in math class. I want you to use this data to predict that if someone has a 90% attendance rate, what is their grade in my class? What would you predict their grade is in the class? All right. So go ahead and pause and try it on your own, and then unpause when you're ready for me to go over it. Okay, hopefully you were able to do this on your own. I still want you to watch me go over it rather quickly. I'm going to enter in the data into Desmos first. All right. One student had an 80% attendance, and they had a 74% in the class. One student had a 60% attendance, and they had a 30% in the class. One student had a 98% attendance, and they had 100. Good job. Another student had an 87% attendance, and they had a 90 in the class. Another student had a 45% attendance, and they only had a 12%. And this person here, 85%, they're coming to school, yet scoring a 23. They're obviously not learning anything or doing anything in class. And then our last student, 80 and a 61. I'm going to run the regression as y1 is almost equal to mx1 plus b. Whoops. Y there. Hold on. Trying to go too fast. Made a typo. Y1. Oh my goodness. We're all over the board here. All right. Y1 is almost equal to mx1. See how I caught my own typo? Make sure you can do that. You won't have me to catch your typos on a test. I don't know what you rounded this to. You could have rounded or the slope to 2. I think it's better to round this to 1.6. So we have a slope. I'm going to write up here so I have a little more space. The slope is equal to 1.6. B is equal to negative 64. And so I can make an equation now in slope-intercept form. Y equals mx plus b. I'm going to plug in 1.6 to m. negative 64 to B, but I'd rather be more specific. Y is equal to your grade in class, and X is equal to your attendance. I'll use an A minus 64. I'll be a good student. I'll define my variables as G equals grade in math, A equals attendance rate. And so now that I have this equation, I better understand the relationship between your grade and your attendance in my class. I can plot this on, or I can plug in. If a student has a 90% attendance rate, I need to plug that into A. And so I'm going to do that. A student's grade is equal to 1.6 times 90 minus 64. 1.6 times 90. Let me try to do this in my head. I know 90 plus 3/5. 90 divided by 5 is 18. 18 times 3 is 54. This is 144 minus 64. 144 minus 64 is equal to 80. So I predict that a student who attends class 90% of the time will score an 80% in my class. Now, is attendance the only thing that determines your grade? No. There are many different things that determine your grade, right? So this just helps us make a prediction. It doesn't mean it's exactly right. It doesn't mean it's exactly right. It just helps us make a prediction, okay? All right. That's it for this video. Hopefully you're able to understand this, wrap your mind around it, and continue to deepen your understanding of linear regressions.